Hello everyone. Today I am going to give my lecture on hydraulic conductivity in heterogeneous and anisotropic porous media. As you may know, the hydraulic conductivity is often anisotropic, which means that it varies with the direction of flow. There are two reasons. The first reason is bedding in sedimentary rocks, which is shown here and also given here. The second reason is preferential flow paths. As these two figures show, preferential flow means that water and its constituents, such as soluble dyes, tracers, and other chemicals, moving by preferred pathways through a porous medium. It has been investigated that this preferential water flow is typically much faster than flow through the other parts of the porous media. In heterogeneous and anisotropic media, the hydraulic conductivity is a tensor, which means that its properties change with direction. So a symmetric matrix, which is given here, is used for hydraulic conductivity in such media. In this matrix, kxx, kyy, and kzz represent the hydraulic conductivity along the x, y, and z directions. As you know, symmetric matrix is a square matrix which is equal to its transpose. Considering a symmetric matrix for hydraulic conductivity, the Darcy's law in heterogeneous and anisotropic porous media can be expressed using these three equations. This equation means that the potential gradient in a particular direction, for example in x direction, can result in water flow in other directions. So this is very important in water flow studies in fractured and porous media. As you know, sedimentary rocks are characterized by bedding, which occurs when layers of sediment with different particle size and thicknesses are deposited on top of each other with horizontal layers. Anisotropy is an important parameter. We consider two components for hydraulic conductivity: horizontal and vertical. In such media, the Darcy's law along the x, y, and z axis can be given by these three equations. Here, kh is the horizontal and kv is the vertical component of hydraulic conductivity. In sedimentary environments, according to my explanation in the previous slide, the basic equations governing groundwater flow for confined and unconfined aquifers are given here. Please note that the flow medium is assumed to be saturated and flow is time dependent. In these equations, the left hand side is the same. SS represent the specific storage for a confined aquifer, and SY is the specific yield of an unconfined aquifer. B represent an average thickness of an unconfined aquifer. KH and KV are the horizontal and vertical components of hydraulic head. T represent time and H is hydraulic head. X, Y, and Z are the Cartesian coordinates. After a brief discussion about hydraulic conductivity in anisotropic environments, let me examine more about hydraulic conductivity in stratified environments. In general, soils in sedimentary environments are layered, so these environments are anisotropic. In such environments, the hydraulic conductivity is different depending on whether the flow is perpendicular or parallel to the stratification. Here we explain two cases. In the first case, the water flow is perpendicular to the stratification. The second case will be discussed later. As these pictures show, the sedimentary environment consists of a number of layers with different thicknesses and permeabilities. I mean, each layer has its own thickness and permeability. As I said, the groundwater flow is perpendicular to the stratification. Here it is necessary to define an average vertical permeability named KMV for the medium. After determining this permeability, one may say that our medium only consists of one layer with a thickness equal to the sum of the thicknesses of layers and with a permeability equal to the average vertical permeability. If so, we can replace this simulated medium with an actual layered environment. If we consider the discharge velocity of water flow perpendicular to the stratification to be Vy, then we can write Vy is equal to Kmv multiplied by I. The hydraulic gradient I in the set of layers can be obtained using this equation. Here dH represents the total head loss. The total thickness of the layers is obtained applying this equation. Z is equal to Z1 plus Z2 plus Z3 and plus Zn. The hydraulic gradient in each of the layers can be calculated using this equation. The hydraulic gradient of the first layer is equal to dH1 over Z1. The rearrangement of this equation gives dH1 is equal to I1 multiplied by Z1. Similarly, dH2 is equal to I2 multiplied by Z2, and finally dHn is equal to In multiplied by Zn, and the total head loss is eventually calculated using this equation. dH is equal to dH1 plus dH2 plus dH3 and plus dHn equal to I1 Z1 plus I2 Z2 plus I3 Z3 and plus In Zn. Under steady flow conditions, according to the continuity equation, the water velocity in vertical direction will be the same in all layers. I mean, Vy, velocity in the vertical direction, is equal to Kmv multiplied by I, which is equal to K1 I1, water velocity in the first layer, equal to K2 I2, water velocity in the second layer, and finally equal to Kn In, water velocity in the nth layer. According to the hydraulic gradient equation for the set of layers, and by replacing the hydraulic gradient in the above equation here, we obtain this equation, and finally we change this equation in terms of the average hydraulic conductivity in vertical direction. So we can write Kmv is equal to Vy multiplied by Z over the total head loss. So the final equation for the average hydraulic conductivity in vertical direction will be KMV is equal to Z over I1Z1 plus I2Z2 plus I3Z3 plus INZN divided by Vy. Considering this equation obtained for the average hydraulic conductivity in the vertical direction, and given that I1 over Vy is equal to 1 over K1, the hydraulic conductivity in the first layer. Similarly, I2 over Vy is equal to 1 over K2, the hydraulic conductivity in the second layer. And finally, In over Vy is equal to 1 over Kn, the hydraulic conductivity in the nth layer. Then we can write Kmv is equal to Z1 plus Z2 plus Z3 plus Zn divided by Z1, the thickness of the first layer, over K1, the hydraulic conductivity of the first layer, plus Z2 over K2 plus Z3 over K3, and plus Zn over Kn. Zn the thickness of the nth layer, and Kn is the hydraulic conductivity of the nth layer. In this case, the total flow rate per unit width is obtained using this equation. In this equation, KMV represents the average hydraulic conductivity in vertical direction. I is the hydraulic gradient for the set of layers, and Z is the total thickness. Okay guys, let's talk about the second scenario. In the second scenario, we assume that the water flow is parallel to the bedding planes. This figure shows several layers of soil with horizontal stratification. The first layer has a thickness of Z1 and hydraulic conductivity of K1. The second layer has a thickness of Z2 and hydraulic conductivity of K2, and the nth layer has a thickness of Zn and hydraulic conductivity of Kn. For the set of layers, the hydraulic gradient I is constant because the head loss is constant for all layers. For the set of layers, we can define an average hydraulic conductivity in horizontal direction. So the flow rate per unit width for each layer can be calculated using these equations. For the first layer, Q1 is equal to K1 multiplied by I multiplied by Z1. For the second layer, Q2 is equal to K2 multiplied by I multiplied by Z2. And finally, for the nth layer, Qn is equal to Kn multiplied by I multiplied by Zn. The total flow rate per unit width of the stratified aquifer Q is calculated using this equation. Q is equal to Q1 plus Q2 plus Q3 plus Qn. We put the mathematical formula related to the flow rate per unit width of each layer using the Darcy's law to get this expression. Considering that the hydraulic gradient I is a common factor in all terms of this equation, then we can write Q is equal to I multiplied by K1 Z1 plus K2 Z2 plus Kn Zn. Considering that the KMH it to be the average horizontal permeability, then for a homogeneous system we can write Q is equal to KMH multiplied by I multiplied by Z. In this equation, Z is the total thickness and I represents the hydraulic gradient for the set of layers, and Q is the total flow rate per unit width of the aquifer. The total flow rate per unit width of the aquifer Q can be calculated using equation number 1 for a stratified aquifer and using equation number 2 for a simulated aquifer with an average horizontal permeability kmh. Considering that equations number 1 and 2 are equivalent to each other, we can then write this expression. The hydraulic gradient I can be removed from both sides to give equation number 4. If the layers have the same thickness, equation number 4 is summarized to equation number 5, and finally equation number 5 can be further summarized to get equation number 6. kmh is equal to k1 plus k2 plus k3 plus kn over n. In this equation, kmh is the average horizontal permeability, n is the number of layers in a stratified aquifer, and k1, k2, k3 and kn are the permeability values for first, second and nth layer. Well, here we have provided an example. We have 4 sedimentary layers with the same thickness equal to 10 meters. These layers are placed on top of each other. The permeability coefficient of the layers is given here. The flow is parallel to the stratification. The aim is to obtain the average horizontal permeability for the set of layers. We use this formula. kmh is equal to k1 plus k2 plus k3 plus kn over n. We sum up the permeability of the layers and divide by the number of layers. The result will be the average horizontal permeability of the layers. I mean kmh is equal to 2 times 10 to power of minus 5 plus 1 times 10 to power of minus 5 plus 3 times 10 to power of minus 5 plus 2 times 10 to power of minus 5 over 4 is equal to 8 times 10 to power of minus 5 over 4 is equal to 2 times 10 to power of minus 5 meter per second. By determining the permeabilities kH and kV, it is possible to convert a homogeneous anisotropic medium to a hypothetical isotropic medium applying the degree of permeability and isotropy, which is equal to square root of kH divided by kV. Therefore, the hypothetical isotropic medium has these components of the permeability coefficient. The horizontal permeability will be kH minus square root of kH over kV, and the vertical permeability will be kV minus square root of kV over kH. There are 2 important notations that we must take into account in heterogeneous environments. Notation 1 is that the vertical permeability kV can be ignored in the soil consisting alternating permeable and impermeable layers, which means kV is equal to 0. The second notation is that if Q to be the real flow rate in an anisotropic medium and Q1 to be flow rate in an hypothetical isotropic soil, then we can write Q over Q1 is equal to KH over KV.